We're going to get started a little early today so that we can get to Chipotle earlier too. So my name is Chris Nicholson. I'll just wait for these guys to get. Hey folks. Hey guys. Hey guys.
Good folks back there.
We're going to start early today. So if you want to join us, that'd be great. So my name is Chris Nicholson. I'm CEO and co-founder of Skyline. Kevin Minogue invited me in because we've been involved in AI, let's say deep artificial neural networks, about 4 years now. So before I start this talk, I want you all to know, many of you are probably more technical than me. You probably know more about cybersecurity than me. I'm not a software engineer, right? But what I'm here to talk to you about is our experiences running an AI startup, deep learning startup, serving some of the largest organizations in the world. And I'll get to what those organizations are in a little bit. I'll talk a little bit about how we've seen them apply deep artificial neural networks and some other algorithms to problems like cybersecurity. So first I'll give you a brief overview of us so you'll know where we're coming from. What's Skyline? We tell venture capitalists that Skyline is Red Hat for AI. Right? What does that mean exactly? It means we make open source software, we bundle it together, and we provide it to our clients in an enterprise distribution. So if you've worked with Red Hat or Cloudera, right, then you kind of know the business model there. So that's what we've got. We've got about 40 employees. They're distributed all over the world, a bunch of them in North America. My co-founder's the technical guy. He lives in Tokyo, so he couldn't be here today. But Adam Gibson is the creator of Deep Learning for J. Deep Learning for J is the most popular deep learning tool for the Java language, for the JVM. Right? Obviously, a lot of data science happens in Python. I'll get to how we interface with that a little later on. So that's Skyline 4 years ago. How many people here have watched the HBO series Silicon Valley? All right, you know what a hacker house is? Do you know what a hacker house is? That's where they live in the movie. I used to live in a hacker house. That's how I met Adam. We lived there for about a year. I had a bunk in a room full of snoring guys. There were 5 other snoring guys in the room. Notice I say other snoring guys. And Adam had a bunk in a room full of snoring guys too. And so we met in this place. We moved there in late 2013, and he was already thinking about building open source machine learning tools. The reason why 2013 was kind of an inflection point for deep learning was because that was the year Google hired Jeff Hinton. Do people here know who Jeff Hinton is? Who's heard of Jeff Hinton? Yeah? Cool. Jeff Hinton is the world's most prominent deep learning researcher. He's been working on neural nets for decades. As many of you probably know, neural nets are actually a decades-old technology. They're very similar to the perceptron, which came out in, I think, the 1950s. But neural networks were getting serious work done on them in the 1980s, and Jeff Hinton was the guy doing it. And he kept on doing it despite a lot of opposition in various sectors in academia, until finally, in the mid-2000s, neural nets started producing astonishing results. Right? And that happened for a number of reasons. One of the reasons why it happened is because the hardware caught up to the algorithms. Right? So as most of you probably know, deep learning happens on GPUs. Right? You can do it on CPUs. Right? You can do it on hundreds of CPUs. But if you want to do it fast, and if you want to iterate through experiments quickly to find the right combination of hyperparameters, you do it on GPUs and you do it on pretty large GPU clusters, right? So each GPU being in itself a massively parallel calculator, and then linking all those massively parallel calculators together to make sure you can perform the linear algebra operations, the matrix multiplications at scale, right? Because those matrix multiplications and adjustments are actually how you train a neural net model. So in any case, I'm digressing. In 2013, Google hired Jeff Hinton. A couple months later, Facebook hired Jan LeCun. Jan LeCun's the number 2 researcher in the world around deep learning. He's now the director of research, AI research at Facebook. Right. So 2013 was the year. I might close this door.
Of course, yes.
But what we need to do is open the back door. Yeah, let's open the back door. There's just a lot of noise in here. So 2013 was the year that businesses started hiring these researchers to apply their work to problems where they could make money from those algorithms. Right. So those 2 big hires caused a lot of people to start asking themselves the question, how can I apply deep neural nets to my business problems? One of those people was my co-founder, Adam Gibson, and what he started looking for were open source tools on the JVM to help him do that. At the time, high quality tools didn't exist. Obviously, neural nets have been around for a while. You can find a lot of open source implementations of neural nets on the internet, But those tools did not work on distributed GPUs. They did not incorporate the latest algorithms. And what that really means is they didn't really scale well. And scale is really important for deep learning because, as you may have heard, deep artificial neural networks are data hungry. They're greedy for it, right? They can produce record-setting accuracy. Their predictions can be very accurate. But for that, they need to be exposed to a lot of data, which means you need a lot of processing power. So where are we today? Or let me take a step back. So Adam started building deep learning for Jay. That evolved into a business model for an open source software company. Now we're selling into companies like this. So we work with SoftBank, Department of Homeland Security, Boeing, and I'll go into a couple of those use cases later. More importantly, we've got a huge install base of people who don't use, right? Because the great thing about open source is that it creates a lot more value than it captures, right? That's part of the ecosystem. We give something to the world. A lot of our users are actually contributing back to our code, right? And you could say that's a virtuous cycle with really high quality assurance because you've got tens of thousands of eyeballs on your code. You could also say that's probably one reason why Linux won the operating system war over Windows, right? So the open source tools today that are focused on that AI layer, ours, TensorFlow, you've probably heard of others, right? They're taking advantage of that virtuous circle. So I'll just get into two of these clients because they're, and at least one of them is kind of tangential to the security problems we're talking about today. So U.S. Department of Homeland Security, what do we do for them? Obviously, what Homeland Security does is it cares about who's coming into the United States and who poses a risk to the United States. They have a pile of traveler manifests to review every day. Right? They have blacklists that they need to match against people whose names may not be spelled the same way all the time. Right? So you need to do this kind of fuzzy matching against those names, and they also want to flag anomalies like, hey, you traveled to Syria a few too many times in the last 2 years. So the nature of our work with the Department of Homeland Security is basically a classification like matching people to their blacklist and flagging these anomalous travelers who may pose a risk. And why is that kind of close to the cybersecurity problems that I think you've come today to hear about? Well, on the very highest level, you can think about kind of the PCAP files or the data packets that are coming into your data centers in a similar way that Homeland Security is thinking about these travelers. Now, I'll get into our limited experience with cybersecurity and also kind of our broader knowledge of what's happening in the field in a second. So why do I talk about anomaly detection in cybersecurity? One of the reasons I'm talking about it is because signature-based cybersecurity is not enough, right? So as you probably know, one of the main ways that cybersecurity or one of the main ways that we kind of keep the bad guys out in cybersecurity these days is we construct a model of what attacks look like, right? We collect signatures, then we go out and look for attacks that match those signatures. Unfortunately, that is not a preventative model, right? That is at best a fast response model, and at worst a very slow response model, right? So the shift we're seeing in the industry today, which is probably happening with a lot of the companies that you're seeing in the hallway, it's happening with companies like Skyland, right? Is that they are what they're doing is they're taking deep artificial neural nets, right? Like we know that cybersecurities are using these tools and algorithms very similar to ours, and in some cases they're using ours because they're open source algorithms. And they're building predictive models, which is to say they're recognizing the malware before it executes in memory, right? They're not waiting for bad things to happen; they're preventing them from happening, right? So that's the shift in the industry today. I believe people estimate we're catching about 30% of all attacks, right? If we're lucky. That number can, there's the potential to raise that number a lot. And some of the firms that are applying deep neural networks to these attacks are saying they're getting double that accuracy, for example, right? So here's an analogy, right? I think the kind of mainstream model, kind of the antivirus McAfee model is cybersecurity software ought to be like firemen, right? They respond to calls. If something bad happens, you send out the team, right? Unfortunately, a lot of times the damage is done by them, right? And that damage can be irrecuperable. And as we saw over the last couple of years with kind of the U.S. election process, the U.S. is under attack, right? Private sector companies are under attack. There's an ongoing cyber war. And not catching the people who are penetrating our systems has enormous consequences at a local and national level. So the promise of these algorithms is to not just prevent things from executing memory and stealing that data, but it is to, excuse me, it is to build predictive models without a large label data set, right? So let me get into kind of different ways to come at this problem. How many of you have built a machine learning model or have built a classifier? Question. 3, 4 of you. Okay, great. So that signature-based model I'm talking about, that's pretty much a classifier, right? What does a classifier mean? It means that I've got, I'll use images as an example. If I'm building an image classifier, I could take a picture of everybody in this room, right? I could get all your names. I could associate your names with the JPEG with that blob of pixels, right? And my algorithm would learn the correlation between the blob of pixels and the string of characters, right? That's a classifier. A classifier requires that I know the name to apply to your blob of pixels, right? Now, that we can do that very accurately. That's called supervised learning, and it's basically a solved problem, right? Like, that's really easy to do every time you go on Facebook and you see your friends' names pop up next to their blob of pixels, right? Facebook is applying supervised learning. It is most likely a deep convolutional network, which is a form of deep learning, to those images. They built a great classifier, and they did that because everybody's been tagging their faces, the names to those faces for a long time. They have an enormous labeled data set, right? In a lot of the problems we want to solve in the world, those enormous labeled data sets don't exist, right? So one of the questions that our clients need to ask themselves after they establish what we call use case clarity or strategic clarity about what they want to solve, right? And that could be, hey, I want to catch cyber attacks. Then the second question is, okay, do you have the data to train an algorithm to do that, right? And the truth is, if they've been using that signature-based model, then great, we can train an algorithm to recognize attacks that have come before. But guess what? Those are not the most interesting attacks. They're certainly not zero-day attacks, right? So a second way to tackle this problem is through anomaly detection, right? And what does anomaly detection do? Anomaly detection works with unlabeled data. The vast majority of the data in the world is unlabeled, and anomaly detection uses its knowledge of what's normal in the data. And luckily, most of the data is normal. Most passengers coming into the States are normal. Most data packets are normal. It learns to reconstruct normal, and by learning to reconstruct normal, it can see what's unusual, right? And kind of a simple way to think about it would be, okay, what's 2 sigmas away from the mean, right? It's not quite that simple, and it's very multidimensional. But that's the idea is what's far away from the mean along certain dimensions, and then it can flag those anomalies for you or for your human analysts, right? Or for a business logic system where you just say, okay, if it's unusual enough, I want to take these actions on it, right? Simple if-then statements. So I'll skip some of the business model stuff. Let's talk about like why AI is possible. I got into it a little bit just a moment ago. So in the mid-2000s, Jeff Hinton started showing really amazing results with deep artificial neural networks. He was applying them to images and to speech recognition, right? And I'll just give you one example of kind of the potential of these algorithms. The state of the art in, say, 2009 for speech recognition was an algorithm that had been constructed over about 30 years. It had 30 years worth of feature engineering that was producing maybe 70% accuracy on kind of recognizing what was happening when someone spoke. In 2009, in 3 weeks, a disciple of Jeff Hinton built a deep neural network that matched that performance. And since then, we've far surpassed that performance, right? So 30 years, 3 weeks, right? The potential is that for these algorithms, given the right data, to get to almost human-level accuracy and sometimes surpass human-level accuracy in a very short amount of time without knowing a lot about what they're looking at. And that's kind of the key, right? Obviously, domain experts are still important, but these algorithms are actually noticing latent factors that go beyond what humans have been taught to perceive and what we can sometimes articulate. So in the late 2000s, Jeff Hinton's team is doing that. They're showing state-of-the-art results And a few years later, Google's ready to pay tens of millions of dollars for his 3-person startup, right? And by 2014, they paid $600 million for a company called DeepMind. That's a think tank in London. Now, what did DeepMind do? Well, DeepMind wasn't doing a whole lot more than winning at video games with something called deep reinforcement learning at the time, right? But a year after their acquisition, DeepMind had produced an algorithm that cut Google's energy costs in cooling its data centers by 40%, right? And if you understand the scale at which Google is operating its data centers, you realize that DeepMind paid for itself in that first year by several X. Okay, so this is kind of, I'll skip some of this stuff, but I'd like to talk about what's happening now in Silicon Valley, how companies like Google, Microsoft, Facebook, and Amazon are using deep learning, and why they're doing that. Obviously, why is they're realizing the potential for superhuman accuracy, or at least greater accuracy, on a lot of problems. And it's not just image recognition problems, although image recognition is cool, right? I think you guys probably don't care that much about image recognition. But I can say, how's Google using it? Well, Google is putting self-driving cars on the road. Actually, they put them on the road last year in Chandler, Arizona, right? Some Fiat Chrysler cars. They're rolling around Chandler, Arizona, carrying what they call early riders around, and those cars are using image recognition to steer themselves. It's much more complicated, but there are image recognition models in those cars. Google has published papers saying they're using deep neural networks to predict CTR. CTR is click-through rate, right? Google's an ad company in addition to a data center company, and what if you can predict CTR, you can serve the ad that's most likely to be clicked, and if you can serve the ad that's most likely to be clicked, you can earn a lot more revenue. And when we look at Google's revenue, it's having a series of blowout quarters. There was a quarter last year where they were up 23% year on year, right? And that's partially because video and mobile ads are up, and it's partially because they're just predicting which ads people want to click on much better, right? So those are some of the use cases, and those use cases directly hit their bottom line, right? So the idea, of course, is that for those use cases when they're generating billions more per year, you can obviously generate enormous economies of scale and offer their services for a lot cheaper and outdo the competition. And that's Amazon's model too, right? So Amazon's quickly catching up with Google, Facebook, and Microsoft to offer to use and also offer some very powerful machine learning tools on AWS. You may have heard of them. There's SageMaker, right? There's MXNet, which is their open source stuff. Works primarily on their public cloud. In any case, these companies are all moving fast, and they're all building AI in a smart way, and they're building it with the necessary ingredients. Some of those ingredients are hard to come by, and I'll talk about what they are in a second. Let me talk briefly about how we see the market. And you can obviously all of you can kind of gauge whether you think this is accurate and where you might fit into that. So these companies I'm talking about, Google, Facebook, Microsoft, we call them tier 1 companies, and by that we just mean they built AI from the ground up, right? Google built a tool called TensorFlow, Facebook has something called PyTorch, Microsoft has CNTK, Amazon has MXNet. Now, they all built open source deep learning tools. They threw those over the wall to the world, and they're using those tools as a recruiting pipeline, right? Because when people start using those, then they kind of offer them jobs, and they know that they've onboarded already. Tier 2 companies, these are companies who, like Wall Street banks, have the quants who are capable of tuning a machine learning solution, tuning a machine learning algorithm. But it doesn't make a lot of sense for them to build their own machine learning framework, right? So that would be any of the top Wall Street banks, Goldman Sachs, JP Morgan, Morgan Stanley. It would be a lot of the sophisticated tech companies that are maybe nevertheless not what we would say the top tier are. So that would be eBay or PayPal, for example. Like they're using, or Yahoo, they're using other people's tools. And then if we go down one step to companies with fewer quants, these folks, they bought into big data, right? They brought in a lot of skills. They probably have a Hadoop cluster, so they've kind of normalized their data. They've broken the data out of silos and brought it into a data lake. They're typically using kind of scalable JVM tools, so Hadoop, Spark, Kafka, Elasticsearch, right? But they don't know how to build machine learning solutions yet. And these two tiers are the companies we work with mostly. The top one doesn't need us, and tier 4 here can't use us yet generally because they usually haven't built out the skills necessary to gather, store, and move data in the right way. And tier 4 is most of the companies in the world. That looks like an isosceles triangle, but like the distribution in the world, in the real world, that triangle has a long, very fat tail, very thin at the top. So I guess I'd like to talk about what you need to build a viable machine learning solution. How many people here think your organization wants to build a machine learning solution in the next year or so? Yeah. Okay. And Manoj, is there a question and answer session baked into this?
Yeah, there's time.
Okay.
When you're done.
Okay. Okay. Cool. We'll do that. All right. So I'll go through this at a high level and maybe give you some war stories about things that some pitfalls we've seen. So the first thing that every company needs is a team, and that team is actually multifaceted. So most companies that are aware of machine learning and want to implement it, they think they need to hire data scientists, and they're mostly right. But data scientists alone are not enough. And one of the reasons why they're not enough is because most data scientists are coming out of backgrounds where they were not taught to think architecturally about software. They don't know how to plug the models they train into a production stack, right? So what we see is that in companies that have really mastered are building effective machine learning solutions, we've got 3 teams involved, right? They've got data engineers, typically JVM people, who have been involved in gathering, storing, and moving the data for quite some time. We've got data scientists who are involved in exploring the data, choosing the algorithms, tuning the algorithms, maybe monitoring their performance. And then finally, they have a DevOps team that has found a way to deploy those algorithms to production, right? So data engineers, data science, DevOps. And this has to be a cross-team thing, right? If just the data scientists build a machine learning solution, a lot of the time that machine learning solution fails. And the dirty secret in my industry is that most data science projects fail, right? And they fail for a lot of different reasons, but one of them is choosing the wrong tools and integrating poorly, right? I'll get into some of the others in a sec. So what do we think, like, when we were kind of looking at what we thought the world needed, right, and why we thought deep learning should exist, we were looking at how companies are choosing software today, right? So open source is a big thing. If you go to JP Morgan, right, their procurement is very strongly oriented towards Hadoop and Spark, right, and away from things like SAS and Informatica that are going to lock them in. So they're obviously they need to be scalable. They believe that the hybrid cloud is the future, right? So it's not, they don't want to get locked into just a public cloud. They don't believe that they'll be 100% on-prem forever, and they're probably going to choose a kind of a negotiating position, distributing their data to multiple clouds, right? Kind of a multi-cloud strategy. Let's see. So that's the tools. The tools just need to work anywhere, and they need to plug into their production stack, which is to say they're not going to choose tools that force them to rip out tens and hundreds of millions of dollars worth of investment, right, that they've already made, usually on the JVM. Finally, you need the data. I wish I had a whiteboard so I could kind of jump around a little bit more here. The data is these 4 things: tools, team, data, and infrastructure. They're all equally necessary, and if you're lacking any of them, you probably won't get machine learning right. Tools and infrastructure have technological solutions, right? You can go out and buy something or choose something that will solve that for you, right? Team and data are a bit harder. So there's data science academies all around the country that are churning out data scientists, right? Like you can, if you're willing to pay the money, you can probably find a data scientist somewhere who will help you start working with algorithms. But they can be hard to find, and they travel in flocks, right? And a few of the top tech companies have really front-run the market, right? They've gathered a lot of the top talent to themselves, and those are the ones I named earlier: Google, Amazon, Microsoft, Facebook. So that job market is correcting. Demand, supply is catching up with demand, right? But it can be a hard slog, especially if you don't already know exactly what you're looking for, to find the right data scientist. Finally, the data itself, there is no technology solution for the data, and no matter how much money you pay, you can't hire the right data, right? Like, getting the right data is the hardest, it's the choke point for getting machine learning right. And if any of you have been watching kind of the travails of IBM Watson, you know that about a year ago, there was a lot of people came out and said, look, IBM Watson isn't really working for us. MD Anderson threw them out. There was some little mini scandals there, and IBM came out very frankly and said, in a lot of these cases, we just didn't have the data we needed, right? And for me, the takeaway for me was machine learning starts with the data, right? You can't bolt machine learning on to data and try to turn the data to a secondary purpose. That will lead to suboptimal results. So when we counsel with people we work with about how to approach this, once they know what their use case is, right, the second question is, okay, do you have the data that correlates to it? And if not, let's get a data strategy, and let's make sure that the data we gather is aligned with the purposes you want to put it to. Right? So that putting data to a secondary use, bolting on machine learning to a data lake that you've just been kind of building over the last 10 years, that can lead to disappointment. Right? We've seen several companies go down that road. Let's see. I think some of this might be a little too simple for you folks, but I'm gonna talk about it. I'm gonna go for this anyway. So here, and maybe how this will be useful is you're gonna go back to your companies and you're gonna say you may say we need to think about machine learning, we need to think about AI, right? And your colleagues may say, well, what is it? How should we think about it? Can you explain it to me? So one thing I can do is I can give you some tools to explain it to your colleagues easily. Right? Because what people understand, they're more likely to engage in. And what people don't understand and are scared of, they're more likely to put on the back burner. Right? So, okay, so the easiest way to think about AI itself, let's just say it's math and code and forget about it for a second, right? Let's pretend it's a black box. There's a three-part explanation, really easy. Data goes into the box, decisions come out of the box, and the decisions are about the data, right? AI makes decisions about the data. Right? And it makes certain kinds of decisions that I can explain now. Deep learning makes three main kinds of decisions. And I think I actually have a slide for this. Here we go. It does classification, it does clustering, and it runs regressions. Right? So what's classification? I mentioned earlier, it helps you put names to faces. Right? That's classification. It labels things. It categorizes things. Right? So for cybersecurity, right, it would be attack or not attack. Right? For fraud detection, fraud or not fraud. Right? For image recognition, right? That's Chris, that's Manoj, Chris, right? Like so it's putting names to things, and in order to put names to things, you need to have a labeled data set to begin with. Right? So let's step back for a second and think about how deep learning works versus other kind of previous forms of AI. With kind of traditional, good old-fashioned AI, what you did was you created the rules. So an expert system in the 1980s was a great, huge system of rules, a pile of nested if-then statements. You created the rules, you gave it the input, and it produced the output, right? So to an expert system, you give it rules and input, it gives you output. Deep learning doesn't work that way. With deep learning, you give it the input, which is the blob of pixels, you give it the output, which is the names, and it finds the rules for you, right? That's the difference in these systems. And so when I talked about the latent factors that deep neural nets can perceive, what I'm saying is they are finding rules that you didn't know to look for, that you didn't know to program. They're adjusting themselves to find the significant features, the significant inputs that will lead them to to make the accurate prediction. So that's classification. And classification is when you're explaining AI, when you're explaining deep learning, classification is usually the easiest use case to explain. It's easy to imagine a picture. It's easy to imagine putting a name to a face. We all need to do it, right? But there are other really important types of problems that it can solve. It can also cluster. So what's clustering? It's grouping. It's detecting similarities. So if you go to Google Photo Search today and you upload a red slipper, right? It's going to show you a red sneaker. and it doesn't even know what slippers and sneakers are, right? You didn't give it a name. It doesn't have a name in its database. All it knows is those red pixels form approximately the same shape, right? So that's clustering. That's creating nameless clusters, detecting similarities. And by the same token, because it can detect similarities, it can detect outliers. It can detect anomalies, right? So that ability to reconstruct what normal is, to understand what it's looking at even when it doesn't have a name, is the foundation of this set of very powerful solutions, right? Where even though we don't know what fraud looks like, we can flag unusual behavior, which correlates with bad behavior, right? So that clustering is kind of is the flip side of anomaly detection, in a sense. And when people are applying these algorithms to things like security, right, you can use certain deep algorithms like centroids, for example. You know what centroids are, to kind of group types of programs, right, without saying exactly what they are, right, and say this type of program ought to be whitelisted, or this type of program ought to be blacklisted. And then finally, I said predictions. What I really meant was regressions, right? So I think everybody in the room knows what linear regression is, right? You can imagine a formula where I have y hat, right? That's my estimate, equals a times x plus b, right? So y hat is my output. That's what I want to get from my algorithm. X is my input. A is the coefficient, right? And b is what we call the bias in deep learning. So this is for this is for continuous values, and numerically continuous values. So here's an example. Let's say I'm a real estate agent in Silicon Valley, and I want to figure out the price of the house, right? One of my chief inputs is going to be the square footage of the house, right? That's my X, right? And the Y is the price of the house. Now, obviously, a 1 square foot house does not cost $1, right? I need a multiplier, right, to relate the X to the Y. So linear regression is with machine learning and kind of making multiple guesses about the relationship between X and Y, we can minimize the error and run a regression line through our scatter plot and find an approximate relationship between the square footage, right, as it grows and the price of that house. Maybe it's 43X, maybe it's something more, right? Interestingly enough, you can think about deep learning as it's actually a multivariate linear algebra problem. You're taking a bunch of inputs, you're multiplying each of them, right? Then you're taking that sum and you're passing it through what we call a nonlinear function, sometimes a sigmoid function, right? Logistic regression, for example. So you're taking this multivariate linear regression, you're passing it through nonlinearity, and then you're doing that many times, right? And you're doing that over what we call several layers. Those layers are actually groups of computations. And because these algorithms have these many layers, we call them deep, right? That's why deep learning is called deep. Deep is a technical term. It just means there are more mathematical operations than in certain other algorithms that we would call shallow, if anybody wanted to brag about using shallow, which they don't. What kinds of data can we use? Well, we can use just about whatever you've got, right? So images and video, sound and voice, text, and then time series data. And the time series data can be pure numeric. It could be like, the easiest way to think about time series data is I've got a thermometer and I'm spitting out temperatures one every second, and those temperatures are time stamped, right? And if I chart those temperatures over time, I'm going to see some structure. I'll see some patterns, right? Kind of some kind of sinusoidal thing where I get top temperature at 1 p.m. and bottom temperature at 3 a.m. And because there is structure there, right? Because there's a repetitive pattern, algorithms can actually make predictions, run the regressions based on the time series that you feed in. Sometimes the time series data, especially in your case, if you're working on this time on cybersecurity, it's not pure numeric. It's going to be alphanumeric stuff like server logs, right? But within those time series, there still may be structure that you can find. Actually, I'd like to ask you a question. Who here can explain to me the difference between, let's say, AI and machine learning?
Machine learning is a type of AI.
It is a type of AI. And can you tell me what differentiates it?
AI can go in like robotics and stuff like that, different fields. Machine learning is software. Yeah, that's all I know.
Yeah. No, that's a good start. I would say both AI and machine learning could be applied to robotics because that's just a sector that you can tackle in different ways. Our understanding, and I'm eager to hear yours as well, our understanding is AI is the umbrella term. Obviously, all machine learning is part of AI, right? Subset, like you said. But what differentiates machine learning from AI is the learning, which is to say, traditional AI can be static, right? Like when I talked about an expert system, I don't know how many of you are familiar with CYC. It's one of the largest knowledge graphs in the world, built by a guy out of Texas. Anyway, a knowledge graph requires a human to come in and enter the rules and transfer their understanding of the world, right, in kind of strings of characters, syntax, and relationships between the nodes on the graph, right? The expert systems are static systems that humans build, and they only change when humans change them, right? So what's a good example? TurboTax is actually an expert system, right? It's an expert system that reflects the tax code. You plug in your numbers, and it spits out what you owe. And in order, when the tax code changes, somebody has to go in and change TurboTax. Machine learning isn't like that, right? Machine learning is actually a program that can adjust itself. And it can adjust itself as you expose it to more data. So machine learning, as you may know, people first really started thinking about machine learning per se in the 1950s. There was a guy named Arthur Samuel at IBM, Bell Labs, and he wanted to teach an algorithm to play checkers better than he could. And he was working through that all through the 50s. By the late 50s, his algorithm was beginning to be, how do you make a program be better than you? Right? How do you give it rules, right, to perform better than you? If you knew the rules, you'd perform that well. Right? So he wanted to make something better than him. And you can, and the workaround to kind of coming up with those rules that you don't know yet is just what I mentioned earlier. Give it the inputs and the outputs, right? And it'll find the rules for you. So Arthur Samuel's algorithm was beating the state champion of Connecticut by 1961, right? And that's one of the, what we could call one of the birth moments of machine learning, alongside Frank Rosenblatt at Cornell, who invented the perceptron, right? Anyway, machine learning algorithms can adjust themselves. What a magical thing, right? Like that's if you think about it enough, you can see why Elon Musk is a little scared of this thing. Obviously, the way they adjust themselves, we define the way they adjust themselves. We give them what we call the objective function, the thing they ought to learn, right? The error they ought to minimize. So we go in and we see, like my image recognition algorithm, it's never going to be Skyland, right? Because it's very narrow AI. All it does is it associates symbols with pixels, right? It doesn't know anything about survival or world domination or human manipulation or anything like that. It's the most narrow thing in the world. But if I give it enough names and I give it enough pixels, it can recognize my friends better than I can, right? And so the landscape of AI now, what AI can do is AI can do a lot of different forms of narrow AI very well. Sometimes better than us if we can give it the right data, right? So it's like a crowd of savants, a crowd of Rain Men, right? None of those Rain Men, like you or me, would navigate the world very well, but they know a few things very well, much better than us. So what's that difference between AI and machine learning? Machine learning algorithms are adjusting themselves; they're dynamic. Whereas good old-fashioned AI, it can be static, right? And if we go one step further, what's the difference between deep learning and machine learning? Well, like I said before, deep learning is just, in the mid-2000s, once we had the compute to test it out, we found that piling on a lot more mathematical operations and recombining our input data in various ways to create what we call a feature hierarchy gave us much more accurate predictions, right? So that pile of additional operations is what we call deep.
You got about 5 minutes left.
You know what? Okay, then why don't we? Why don't you guys talk? Why don't you folks talk to me? What should I tell you that I haven't talked about yet?
Yeah. So one thing I was kind of curious, because I mean, you're coming at this from very specifically deep learning, right?
Yeah.
As opposed to other machine learning, like you're saying, like
Yeah.
just basic classifier algorithms and some trained machine learning.
Yeah.
Is one of the problems specific to the security domain in doing machine learning
Yeah.
is and where you're running into issues when, so I've had the experience of being a SME working with data scientists.
Yeah.
And the wall they had to get over. And these are people who knew the machine learning, right?
Yeah.
But they were used to working on problems in domains where, like, it's about the features per observation. So that's one thing.
Mm-hmm.
So I'm curious about the difference between regular, we'll call it regular machine learning, sort of your differentiation, versus how well like deep learning does with this.
Mm-hmm.
One of the issues is that, for example, if you were trying to do, you're saying classifier on files,
Mm-hmm.
Some of these traditional problems you're talking about, the sort of problems you see in academia when people are learning to be data scientists, like facial recognition or whatever, you maybe have 10 features per observation, right?
Mm-hmm.
Or however, whatever that number is. Maybe it's 100.
Yeah.
But the orders of magnitude for something like differentiating whether a PDF file is malicious or not, or a PE file is malicious or not, like in any of the antivirus companies that have been using you would call traditional machine learning to do that for a while.
Yeah.
They're using orders of magnitude more. You need at least like 10,000, like for a PE file. There's like 10,000 F-Secure company in Finland. They use like 10,000 plus features per observation to determine that. And so when you're talking about, and I agree wholeheartedly from what I've seen, I thought it was like what you're saying about you have to have the data. I mean, as you said, you kind of have to have the data. But then you also need like millions. I mean, they're using millions of observations.
Yeah.
Because deep learning, one of the things that I want to get your take on, because I've seen this in policy, like when you start talking to management and policy circles with the financial sector, and also in government. I mean, people are overseeing cybersecurity. Okay, but at that management level, right? They're already realizing or being told that there's this data issue. You have to have the data, and or projects are failing, like you talked about. And people are coming back, especially data scientists, and saying, "But deep learning,
it's not a cure-all.
Is that true, or is it not true?
It's not a cure-all.
Speak to that features versus observations.
I can. And there's really a spectrum here. There are people who will say it's a cure-all, the reason why people are excited about deep learning is that it scales really well with big data, right? Meaning, if you've got huge data, it can probably learn a lot. And that's true with other algorithms too, obviously. Like a bad algorithm with lots of data is better than a good algorithm with very little data. But I think the gist of your problem, of your question here is, how do we process that data before we feed it to the algorithm, right? Can we give it to the algorithm raw? Or do we have to identify features that it should look for, like the 10,000 things that your Finnish company is doing? And the truth is, 80% of the work is still in ETL, right? 80% of the work is still in building the data pipelines. So everybody's talking about the cool new algorithms, right? But you really have to be gathering the data, normalizing and standardizing it, and sometimes what I call it cheating, doing some feature engineering to make life a little easier on your algorithms, right? So, sure, you've got PDFs that might be 100 pages of raw text. There's a couple ways of going about that. Like, let's say what we see companies doing is a combination of some of the feature engineering, and all feature engineering is a hard rule, right? There's an expert system aspect to feature engineering. Whenever you do it, what we see them doing is plunking down rules-based systems alongside deep learning, right? For a couple different reasons. So the rules systems are really good for whitelists and blacklists. Things you never want to do, things you always want to do, right? So I'm a bank, and the feds tell me if somebody gives you a $10,000 cash deposit, you got to report it to me. I don't want to be right 98% of the time. You know, I want to obey the law 100% of the time, and I can make a rule to make sure my tellers in the bank make those reports, right? So that's an example where you have a simple situation in the world, and a rules-based engine is very useful. But with these PDFs that you're talking about, a lot of times you need really complex sets of rules, right? That rely on the context of the words, right? To figure out what's happening in the document. You need to be extracting named entities from the document, all kinds of other things. And rules engines over time, especially when you get 10,000 rules, become unwieldy. You can no longer push them forward. And in fact, they become self-contradicting, right? So what you really want is an algorithm that's going to keep on changing as it's exposed to more data alongside the things you already know should or should not happen, right? So we see people using both at once. Yeah, there are significant advantages to be had by some feature engineering, like you said. But there are also things that humans will never know to look for, right? And that's where deep learning comes in. Does that help?
Well, I guess what I'm saying is, yes, I mean, the big advantage of alleviating that need for labeling, but the orders of magnitude in terms of features, for the types of problems that you're used to dealing with, was, I guess, my question. It's like the example that you were using of the work you did for DHS, that's not like a huge number of features, I'm guessing.
It actually can be. It can be, because we're not just taking traveler manifests, we're associating them, for example, with social media profiles, which is actually blobs of text. Right? So, and as soon as you get into blobs of text, you're basically talking unstructured data. You can turn that unstructured data into 10,000 features if you want to, or you could figure out a way to
natural language processing.
Yes, exactly. Yeah. So a lot of people don't talk about it quite as much, but a lot of natural language processing these days is actually drifting towards deep learning and away from the 10,000 rules.
But don't you need both of them? In a lot of sense. To get a second, because I mean, you have to constrain the deep learning. You start it with the rule sets, and then let it kind of get its bearing, and then let it come back and attack itself.
Yeah, I mean, there are really two different approaches to the problem. So it's not always easy to kind of drift from one to the other. You'll end up with two different models that you probably need to train to. And so what in NLP, deep learning is now the state of the art for things like machine translation, right? So Google, everybody who does machine translation is using deep neural networks, and they're doing really well at that. And what we found is that the fewer rules and assumptions that we impose on those algorithms, the better they do. So right now, the only feature Google's algorithm looks for is white spaces. It just wants to know when there's a new word, right? The rest doesn't matter. No parts of speech, right? No syntactical rules, right? Chomsky's out the window. Yeah. So.
I think that's about time. Yeah,
We're about time. Done?
Yeah, we're
okay,
good.
Cool.
So.
Great. Thanks, everybody. I'll be around all day, so feel free to come up and chat with me.